NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video. Today we're going to explore and prove the second law of radicals, which is a fundamental rule when working with exponents and radicals. Let's start with the theorem statement. The second law of radicals states that for any real number a and any integer m, the nth root of a raised to the power of m equals the nth root of a raised to the power of m. In mathematical notation, we write this as, for all in R m in z, the nth root of a raised to the power of m equals the nth root of a to the power m. This equality is defined where the nth root of a exists. Now let's prove this theorem. We'll work through this step by step using properties of exponents and roots. For our first step, let's start with the left side of our equation, the nth root of a raised to the power of m. Recall that the nth root of a can be written as a to the power of 1 over n, so we can rewrite this as a to the power of 1 over n, all raised to the power of m. For our second step, we'll apply the power rule of exponents, which states that when we have an expression raised to a power and that entire result is raised to another power, we multiply the exponents. So, a to the power of 1 over n, all raised to the power of m, equals a to the power of m times 1 over n. For step 3, we'll use another property of exponents. A raised to the power of m over n can be written as a to the power of m, all raised to the power of 1 over n. So we get a to the power of m, all under the nth root. For our final step, we'll use the definition of the nth root again, but in reverse. A to the power of m, all raised to the power of 1 over n, can be written as the nth root of a to the power of m. And that gives us exactly what we wanted to prove. The nth root of a raised to the power of m equals the nth root of a to the power m. Welcome to this math lesson, where we'll learn how to simplify expressions involving exponents and radicals. Today, we'll focus specifically on powers of radical expressions and how to apply the laws of exponents and radicals to simplify them. Let's look at our first example. For this example, we have the fifth root of 3 raised to the power of 2. When we have a radical expression raised to a power, we can apply the second law of radicals, which states that when a radical is raised to a power, the exponent can be moved inside the radical, multiplying the radicand by that exponent. Now we can simplify what's inside the radical by calculating 3 squared, which is 9. So our fifth root of 3 squared becomes the fifth root of 9. And that's our final answer for this example. The fifth root of 9 cannot be simplified further. Let's move on to our second example. Here we have the cube root of -2 raised to the power of 5. Let's apply the same rule as before, moving the exponent 5 inside the cube root. Now, we compute -2 raised to the power of 5. Since -2 to an odd power gives a negative result, we get -32. For cube roots, we can extract the negative sign from inside the radical, which gives us negative cube root of 32. This is our final answer. The cube root of 32 cannot be simplified further, so we have negative cube root of 32. Let's examine our third and final example. This example is a bit different because we have a negative exponent. We'll still apply the same second law of radicals, moving the exponent -2 inside the cube root. When we have a negative exponent, we can rewrite it as 1 over 7 squared. This allows us to work with positive exponents instead. Now we can simplify by computing 7 squared, which is 49. So we have the cube root of 1 over 49. And this is our final answer. The cube root of 1 over 49 cannot be simplified further. We want to find the value of the expression root 5 raised to the power of 3. To solve this problem, we'll use the power of a radical rule. When we have a radical raised to a power, we can move the exponent inside the radical. Specifically, if we have the nth root of x raised to the power of m, this equals the nth root of x to the power of m. Now, let's apply this rule to our problem. The square root of 5 raised to the power of 3 equals the square root of 5 cubed. Next, let's calculate 5 cubed, which is 5 times 5 times 5, which equals 125. So we have the square root of 125. Finally, we need to find the square root of 125. The square root of 125 equals 5 root 5. Let's move on to our second example. We want to find the value of the eighth root of -2 raised to the power of 8. Again, We'll use the power of a radical rule. When a radical is raised to a power equal to its index, the radical disappears, and we're left with the expression inside the radical. Let's apply this rule to our problem. The eighth root of -2 raised to the power of 8 equals -2 to the power of 8 divided by 8, which is simply -2. Let's compute -2 to the power of 8. We know that -2 to the power of 8 is equal to the eighth power of -2, which equals 2 to the power of 8, because the negative sign raised to an even power becomes positive. 2 to the power of 8 equals 256. Now, we need to find the eighth root of 256. Since the eighth root of 2 to the power of 8 is exactly 2, the eighth root of 256 equals 2. Let's look at one more example. We want to find the value of the 2kth root of -5 raised to the power of 2k. We'll use the same rule as before, but this time with a variable k in the index. When the power equals the index of the radical disappears, and we're left with the expression inside. Now let's simplify -5 raised to the power of 2k. Since 2k is always even regardless of what k is, -5 raised to an even power will be positive. So -5 to the power of 2k equals 5 to the power of 2k. Finally, we simplify the expression. The 2kth root of 5 to the power of 2k equals 5, because the power and the index of the radical are equal. Let's summarize what we've learned in this lesson. First, when a radical is raised to a power, we can move the exponent inside the radical. Second, when the power equals the index of the radical disappears, and we're left with the expression inside. Third, be careful with negative numbers raised to powers. Remember that negative numbers raised to even powers become positive. These rules will help you simplify complex radical expressions efficiently. We need to find the value of -square root of 2 raised to the 4th power. For our first step, we notice that the exponent is 4, which is an even number. When we raise a negative number to an even power, the result is always positive. This is because the negative signs cancel out in pairs. So -square root of 2 raised to the 4th power equals square root of 2 raised to the 4th power. Next, we'll apply a property of powers and roots. When we have a root raised to a power, we can rewrite it as a root of that power. In this case, square root of 2 raised to the 4th power equals the square root of 2 raised to the 4th power. Now, let's evaluate the power inside the radical. 2 to the 4th power equals 16. But we can also write this in a different way. 2 to the 4th power equals 2 squared. This will help us in the next step. Since we have a square root of a perfect square, we can simplify this. The square root of a squared quantity equals the quantity itself. So the square root of 2 squared equals 2 squared. Finally, we compute 2 squared, which equals 4. So the value of -square root of 2 raised to the 4th power equals 4. Let's move on to our second example. Find the value of the 5th root of 3 raised to the 7th power. First, we'll apply the same property we used earlier. When we have a root raised to a power, we can rewrite it as a root of that power. So the 5th root of 3 raised to the 7th power equals the 5th root of 3 raised to the 7th power. Now, we need to work with the expression inside the radical. Let's factor 3 to the 7th power as 3 to the 5th power times 3 squared. This factorization will allow us to extract a part from the radical. Now we can use a property of roots. The 5th root of a perfect 5th power equals the base. So the 5th root of 3 to the 5th power equals 3. Therefore, we can extract the 3 to the 5th power from the radical, leaving us with 3 times the 5th root of 3 squared. Let's do one more example. Find the value of the cube root of -3 raised to the 2nd power. First, we'll apply the same property we've been using. When we have a root raised to a power, we can rewrite it as a root of that power. So the cube root of -3 squared equals the cube root of -3 squared. Now, let's compute the power inside the radical. -3 squared equals 9. So we have the cube root of 9. This is our final answer, as we cannot simplify the cube root of 9 further without using decimals. Let's begin with our example. The 6th root of -4 times -4 squared times -4 cubed, all raised to the 2nd power. To solve this expression, we'll work step by step. First, Let's combine all the factors under the sixth root into a single power of -4. We'll use the product to power rule, which states that when we multiply powers with the same base, we add the exponents. Now, let's simplify what's inside the sixth root. We have -4 to the first power plus -4 squared plus -4 cubed. So we're adding the exponents, 1 plus 2 plus 3, which gives us -4 to the sixth power. Now, we need to deal with the outer exponent. We'll use the power of a root rule, which states that when we raise a root to a power, we can multiply the exponents inside the root. Let's simplify this expression further. We can multiply 6 and 2 to get the exponent inside the root. According to the exponent multiplication rule, when we have a power raised to another power, we multiply the exponents. Now we can see that the expression has simplified to the sixth root of -4 to the 12th power. We can further simplify this by recognizing that we can rewrite the exponent 12 as 2 times 6. We'll use the nth root of nth power rule, which states that the nth root of a quantity raised to the nth power is simply that quantity. Now we're almost done. Let's compute the final result. The square of -4 is 16. So our final answer is 16. We need to simplify the radical expression cube root of -4, all raised to the fifth power. Let's follow the algorithm shown in our example step by step. First, we'll move the exponent inside the radical. When we do this, we multiply the cube root by the power 5, giving us the cube root of -4 raised to the fifth power. In the second step, we'll calculate -4 to the fifth power. When we raise a negative number to an odd power, the result is still negative. So -4 to the fifth power is -4 to the fifth power. For our third step, we need to handle the negative sign carefully. When taking the cube root of a negative number, we get a negative result because cubes of negative numbers are negative. So the cube root of -4 to the fifth power equals negative cube root of 4 to the fifth power. In the fourth step, we'll rewrite 4 as 2 squared. So 4 to the fifth power becomes 2 squared to the fifth power. For the fifth step, we apply the rule of powers. When you raise a power to another power, you multiply the exponents. So 2 squared to the fifth power equals 2 to the power of 2 times 5, which is 2 to the 10th power. Moving to the sixth step, we apply a property of radicals. We can rewrite the expression by splitting the exponent. Here, we rewrite 2 to the 10th power as 2 to the 9th power times 2. For the seventh step, we'll rewrite 2 to the 9th power as 2 cubed to the third power. We do this because when we have a cube root, we can simplify powers of 3 more easily. Now for the eighth step, we apply another property of radicals. For the cube root of a cube value, we can remove both the cube root and the cube power, leaving us with the base. So the cube root of 2 cubed to the third power equals 2 cubed, which equals 8. For our final step, we calculate 2 cubed, which equals 8. So our answer becomes -8 times the cube root of 2. Let's move on to our second example. This time, we need to simplify the cube root of -a squared, all raised to the fourth power. Let's follow the same algorithm as before, starting with the first step. First, we move the exponent inside the radical by multiplying the power of the cube root by 4. This gives us the cube root of -a squared to the fourth power. Now for the second step, we need to calculate -a squared to the fourth power. When we raise a negative number to an even power, the result is positive. So -a squared to the fourth power equals a squared to the fourth power, or a to the eighth power. For the third step, we'll separate the power of a to make it easier to work with the cube root. We can express a to the eighth power as a to the sixth power times a squared. For the fourth step, we'll rewrite a to the sixth power as a squared to the third power. This will help us simplify the cube root. For the fifth and final step, we apply the property that the cube root of a value cubed equals that value. So the cube root of a squared cubed times a squared equals a squared times a squared to the power of 1/3, which we can write as a squared times the cube root of a squared. Let's start solving step by step. First, we'll apply a property of radicals that will help us understand what happens when we raise a radical expression to a power. When we have the nth root of an expression raised to a power m, it's equal to the nth root of that expression raised to the power of m. Now, we need to apply the power property to distribute the exponent 3 to each term inside the parentheses. This means we multiply each exponent inside by 3. When we raise a product to a power, we raise each factor to that power and then multiply them. Now, let's compute the exponents. 3 times 3 equals 9, and 2 times 3 equals 6. So we have a to the power of 9 and b to the power of 6 under the fifth root. Next, we need to recognize that we can rewrite this as a to the power of 9 can be written as a to the power of 5 plus 4. And b to the power of 6 can be written as b to the power of 5 plus 1. This helps us extract terms from under the radical. Using the property of powers, we can split this into the product of a to the power of 5, a to the power of 4, b to the power of 5, and b to the power of 1. Now, we can use another property of radicals to separate the terms under the fifth root. When we have a product under a radical, it equals the product of the separate radicals. Using the property that the nth root of x to the power of n equals x, we can simplify two of our terms. The fifth root of a to the fifth power equals a. The fifth root of b to the fifth power equals b. Finally, we rearrange the terms to get our simplified expression. We can write this as a times b times the fifth root of a to the fourth power times b to the first power, or more simply, a times b times the fifth root of a to the fourth power times b. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.